No, I was I got to the point where I was 197. I was like, no, 175. Did you?
I was 220.
All right, folks. For some reason my phone didn't go off, but it's 2 o'clock. Let's get started. So first we're going to review. So go ahead and scan down the questions and be able to answer them with your neighbor. So talk to your neighbor. You all have a neighbor somewhere near you, so chitty chat for the next couple of minutes. And then we will review a little bit together, and then we'll continue. And I hope everyone has their TI calculators with them, because we will be doing lots of calculator methods today where we're solving systems using our calculator rather than those long hand calculations. All right. So take a couple minutes, folks, turn to your neighbor, review the answer to these questions, and then we'll get started together as a group.
So let's solve the system.
I got a new phone too. I don't want to go home. I will come out first.
Nice. Well, my last one,
I have totally paid off now. But my back camera cracked. I went to Apple Dog, I'm sorry, and I went to Google, they're like, they can fix the camera itself, but not the glass. I was gonna get it, but I didn't want to transfer all the information. Yeah, I lost one. That's why I think.
like everything's on my laptop, but I lost it on my phone.
And then they have like, their gigabytes increase.
Oh, it's
Yeah, the smallest is 64.
I do. For an
That's all I'm doing with the time.
I just decided to get the auto. Go home.
You look over these things.
What does it mean to solve
All right, folks. Let's review. Shall we? Everyone, let's come back together. Number one. What does it mean to solve a system of equations? There's 2 answers. I'll take one of the answers. What's one answer to the question? What does it mean to solve a system of equations?
to find the coordinate and the equation is true?
Yeah, very good. That is the mathematical answer, is that you're going to have 2 different equations, maybe 2x plus 3y equals 6, and then you have another equation, negative 5x minus 4y equals 2, and you want to find the coordinate that you can plug in to both of them, and then both equations become true. That's the technical definition. What's the other definition? Yes, the visual point of intersection, that wherever those 2 lines are, they intersect somewhere, and that point of intersection is the coordinate x, y that you plug in to make both of those equations true. Okay, and what is a matrix? What is a matrix? How would you say it, David? What's a matrix? It's
Big blank right now.
well, let's see, how would you describe it then?
Oh, I don't know.
Multiplying 2.
2 equations.
Let me look at my notes.
Sure. No, I mean, just describe it off the cuff. What am I going to put in here?
Something.
Numbers, right? And how are they arranged? In a circle?
Yeah.
Rows and columns. There it is. So we have some numbers in a row, 5, 4, -3, and then another row, maybe 2, 7, 8, and you've got 2 rows and 3 columns, and so that's a matrix, right? And these numbers represent something. They could represent the x, y number of a system of equations like this. But it could represent cookies, it could represent any number of things. Okay, so that's a matrix. What row operations are you allowed to do? Remember, there are 3 things we're allowed to do. What's one thing we're allowed to do? Yeah, you can multiply or divide a whole row. So if that's what you want to do, you can multiply through or divide through a whole row by a single number. That's one thing you can do. What's another thing you're allowed to do?
Add rows. Right.
You can add rows together. Exactly right. You can just like add this row into that row. So if I were to add the top row into the bottom row, I would keep the top row just as it is. But then I would add it into the bottom row. So 5 plus 2 would be 7, and 4 plus 7 would be 11, and -3 plus 8 would be 5. And so I just added one row into another row. So you can add rows.
Can we switch?
And finally, you can just switch. You can just swap or switch the top and bottom row so that one is now on top and the other one's on bottom. So that's it. That's all you're allowed to do. So then what is the goal of Gauss-Jordan form? Why would we do these 3 manipulations? What do we ultimately hope? If I were to write down goal here, what's our ultimate hope for what a matrix will look like?
Diagonal ones.
They'll have a diagonal of 1s, zeros, and then these numbers over here are the coordinate solutions, the actual solutions we're looking for that you plug into the original equations to make them true. Okay, great. So that's our goal. It's called Gauss-Jordan form. And then how do we define the size of a matrix? Like what's the size of this matrix right here? 2 rows. 2 rows and 3 columns. So we go row by column. So that's the size of a matrix, row by column. And then when can you add matrices? When are you allowed to add 2 matrices? Like, can I add these 2 together if I wanted to?
Is it when the rows and columns match up?
Yeah, the size has to be the same. So you can only add matrices if the sizes are the exact same. Then you get added 2 matrices. What about the last one? When can you multiply 2 matrices? So like, let's say that this was my matrix, a 2 by 5, and I want to multiply that by a 5 by 7.
When the 2 inner numbers are the same?
Yeah, these 2 have to match. And then what will the result be?
The 2 outer numbers.
Yeah, it'll be the 2 outer numbers. Yep, so that's when you're allowed to multiply 2 matrices together.
So what I say when the column and the row matches?
Yeah, when the first one's column matches the second one's row, then you can multiply, and the result will be the first one's row and the second one's column. Yep. All right, well, so we did cover quite a bit of material about matrices last time. We did a few solutions by hand. Everyone was really excited about that. You went home and you wrote your parents about it, and your friends. You posted on Facebook. You're like, I just did Gauss-Jordan form today. Right? That's what you all did, I figured. All right. So now today we get to see, now, by the way, the Gauss-Jordan methodology, we're going to continue doing that for months. Well, okay, just a month. Okay, we're going to do some more of the manipulations. But the first thing we'll do today is pick up where we left off and just learn how to use our calculator. And the calculator will solve a matrix for you without having to go through all that Gauss-Jordan business. Okay, so here we are. Today is January 22nd. It has us starting chapter 17. We're going to finish chapter 2, then we'll do chapter 17. And we have this day built in as a catch-up day, so whatever we don't finish from chapter 7, we'll finish next time. And we can look at your practice test, and then the next week you actually have your test. Today, you do have something due. Your chapter 1 work is due today on my math lab. So tonight by midnight, you should have your chapter 1 work in. Just so you know, if you don't finish it by tonight, I think there's just some trivial penalty. Like any problem you do after midnight tonight, you lose 30% or something like that. So whatever you complete by midnight tonight, you get that credit. And whatever you finish after midnight tonight, it docks you by like 30%. So no matter what, you should still finish all of it, right? If you don't finish by midnight, still finish it. Because doing those problems are going to help you get ready for your test. All right, and then the chapter 2 homework, however, since we're finishing it today, the chapter 2 homework won't be due until the day of the test along with chapter 17 homework. Ready? Okay, so jokes. Did I forget to tell you a joke here?
We heard all the jokes.
Yeah, okay, I did. Okay, well, I'll tell you the one about the dentist. I need to come up with new jokes for you guys because I didn't heard this one. When did the man or woman go to the dentist? At 2:30. 2:30. All right. I really will make a point of getting you some new jokes. Okay, so here we are. We were talking about solving systems of equations. You can guess, you can graph, you can substitute, you can eliminate, and then you can do matrix methods. The only matrix method we learned manipulations in order to turn a matrix like this into a matrix like this, and then you have the answer. Fortunately, today we get to learn a new matrix method called an inverse. So everybody, you're looking at your chapter 2 packet, and I don't know if I give you a spot on the packet to write. Let me see, where are we? It's up at the top of the page, and it just says section 2.5 matrix inverses. Okay, so notice you have a lot of room down here on the bottom. Tons of room down here. Just come down here and let's discuss what the word inverse means. David, you forgot it at home. Well, David, let's just see if I have an extra one. My extra packets typically cost more than the original packet. How much? Oh, a lot more.
That's 25 cents. More than your tuition.
Yep. Let's see. Oh, here we go. Yeah, I do have a couple extras. There you go. Does anyone else need one? Okay.
You said chapter 2, right?
Yeah, chapter 2. We're finishing chapter 2. Okay, so what does it mean? What does the word inverse mean? Well, first of all, just as a simple use of language, inverse operations come in pairs and they cancel each other out. So like plus and minus. Those are inverse operations. They cancel each other out. If you add 5 and subtract 5, you've done nothing. And then what's another pair of inverse operations? Yeah, multiply and divide. Those cancel each other out. If you multiply by 2 and then divide by 2, you did nothing. And then what's another pair of inverse operations? Is that the wrong one?
Maybe chapter 1.
Did? Oh. What's another pair of inverse operations? Add, subtract, multiply, divide, and then?
Square root.
Yeah, square and square root. David. That's chapter 1 notes. Oh, boy, are you lucky. I do have it. Okay, so the last one was square and square root. That's right, that's the practice. Okay, so square and square root. So x squared and square root of x. These are all inverse operations because they cancel each other out. So for instance, if I gave you the equation x plus 3 equals 5, how would you solve it? You can subtract 3 from both sides, but what you could say is you do the inverse operation to both sides. So since we're adding 3 here, you do the inverse, and then you get your answer. Likewise, if I had, say, 5x equals 10, then what would you do to solve it? Yeah, you divide by 5, which is the inverse operation of multiplication. So you divide by 5, and then you get your answer. Okay, so that's enough to say, how are we going to use inverses now? Well, let's just take a look here. If I take a system of equations, such as 2x plus 3y equals 8, and then negative 3x plus 2y equals 10, the way I can split this up is to call this matrix of numbers, I'm going to call that matrix A. So A is just the matrix 2, 3, oh boy, I chose terrible numbers. Instead of 3 and 2, let's choose something completely different, like 8. I already chose an 8. Oh my gosh. How about we choose a 6 and then a 7? There we go. So my one matrix is 2, 3, negative 6, negative, and 7. That's my A matrix. And then I'm going to call this one, my other matrix, my B matrix. So there's B equals 8 and 10. And so what I could say now is that if I multiplied AX equals B, that would actually give me the product of 2, 3, negative 6, and 7 times the variables x and y, which is equal to the coefficients 8 and 10. Okay, this is just an example, all right? But what I'm showing you here is that I take the coefficients of my system, which is just the coefficients that were on the x and the y, then you multiply by the simple matrix xy, and then that should equal the simple matrix 8, 10. Let's see if that even works. Oh, good idea. Let's see if this even works. If I have this matrix, what's the size of that matrix? 2 by 2. So I have a 2 by 2 matrix. Oh, much better. 2 by 2 matrix. And I want to multiply it times what's the size of this matrix, xy? Yeah, well, it's rows. 2 rows, 1 column. So it's a 2 by 1. Okay, so am I allowed to multiply them? Yeah, and what will the result be? A 2 by 1? And is that the result that I get? Do I get another 2 by 1? Yeah. So this is a valid way of capturing the information from a system, which we would otherwise just graph or do elimination or do substitution. But now I can write it as a simple matrix A, which is just the coefficients from the x and the y, a variable matrix, which is the 2 variables we want to solve for, and then the answer matrix, which is what those 2 equations were equal to, the 8 and the 10. For example, here's the key thing you need to have on your page, if you write nothing else, is if you have a matrix A times the matrix X, and it equals the matrix B, and you want to solve, if this was just an equation, how would you normally solve this equation? Like if I already gave an example. Let's say you had 3x equals 9. What would you do? You divide by 3. That is, do the inverse on both sides. So now, same thing. If it was algebra, ax equals b, you would divide both sides by a, right? And you get x equals b over a. But that's if you were doing algebra, where b and a represented just numbers. Right now, we're saying that a is a matrix and b is a matrix. So if we want to solve for x, which is what we want to do, right? We want to solve for the variables x and y. Then right now what we have is x is being multiplied by the matrix A. We would now need to multiply by the inverse of A. And that's what we're going to do. So I'm going to multiply A inverse to the left there. And over here with B, I also have to multiply to the left, A inverse. And then the A inverse and the A cancel out, and you have x equals A inverse B. And now it's going to be the answer to our matrix problem. I should write that again so you have all 3 steps. So you start with ax equals b, and then what you do is you multiply on the left A inverse on both sides. Because remember, that's the fundamental rule of algebra. You can do anything you want so long as you do it to both sides. And what I'm doing now is I'm going to multiply the left-hand side of each of these expressions by A inverse. So A to the -1 means inverse. And A inverse times A should cancel out, much like these inverse operations cancel out. And so over here, you just have x, which is the variable you're looking for. And over here, you're going to multiply A inverse times B. We need to do an example to really see what this is going to look like. But that's the main idea. And in fact, maybe we're going to get rid of some of this stuff and write that up as our main idea, so that we can see what we're doing to solve with inverses. So here's our technique today. Solve with inverses. Given ax equals b, that's just some system, then x equals A inverse times b. Then what you would do is find the inverse matrix of A, multiply it times b, and that's literally going to give you the answer. So I think maybe the best thing to do right now would be to go ahead and try it. So what's the first problem here? It says, decide whether the matrices are inverses of each other. And it says, check to see if their product is the identity matrix. Does everyone have that? Okay. So first of all, what would it mean for 2 things to be inverses of each other? So let's go back to our normal operations, add, subtract, multiply, divide. Let's say, oh, this is not great. Oh, that first marker was just terrible. Oh no. Why do they even make markers like that? It's terrible. Everyone, let's go home. Okay, we're staying for just another 2 hours and 40 minutes. Okay, let's say that I start with the number 1, and then I add 6 to it, and I subtract 6 from it. I get back 1. So the plus 6 and the minus 6 cancel each other out, and nothing happens. Likewise, if I start with 1, and then I multiply by 7, and then I divide by 7, I still end up with 1. And then if I start with 1, and then I square it, and I square root it, I still end up with 1. So there's the notion that these things are canceling out. So what I'd like everyone to do is, if you take 2 matrices that are inverses of each other, you should be able to multiply them together, and they should equal 1, which as a matrix is the matrix solution that we're looking for, which is the diagonal of 1s with zeros everywhere else. So if you can multiply a matrix times another matrix and you get this, the Gauss-Jordan form, that means that these two matrices are inverses of each other. You could call this matrix A, and this matrix would be A inverse. So let's try that on your calculator. Remember to take your calculator. By the way, who doesn't have their calculator? Does everyone have one? Michelle, you have yours? Super. Luis, you have yours. Simon, you have yours. David has his. You have your calculator. No, you can't. Does that one not work?
Yeah, this one.
Well, let's give it a shot. Okay. So everybody, remember, how do you go in and type all this in? So you have to go into matrix. So second, and notice that button that you've been clicking. What's the button that you push to get to the matrix? That's x inverse. That's x to the negative 1. That literally is the inverse button on your calculator. So x to the negative 1, just like a to the negative 1 means inverse. So you hit second, x to the negative 1. Now you're in your matrices. You click to the right to get to edit. And so let's first put in a 2 by 2 matrix right here, 5, 3, 3, 2. So make sure it's 2 by 2, and then you type in the numbers 5, 3, 3, 2, and there's your first matrix. Then I'll hit second quit. Go down and edit matrix B. That's also a 2 by 2 matrix. So I hit 2, 2, and then I'll type in the numbers 2, negative 3, 5. And when you're all done, you should have 2 different matrices now put into your calculator. And if you now go second matrix, and you're just going to choose matrix A and then matrix B and multiply them together. So I'm going to do matrix A, and then the normal multiplication button. So it's just A times, go back, second matrix, choose matrix B, and what you're going to see on your calculator is A times B. But keep in mind that we're really multiplying these 2 matrices together. And if you hit enter, what do you get?
1, 0, 0, 1.
Yeah, you do indeed get it. So this is the definition of when 2 matrices are inverses. I'm just going to walk around the room, and I want to see your calculator say 1001 so that I can see you got it in there. Oh, super. Oh, super. Oh, dandy. Oh, look at yours with all the decimals. Do you want to turn that on?
I was going to right now.
Oh, you already know how to?
Yeah, you can do it.
If you know how, I'll let you do it. Did it work out? Oh, good. All right. Boy, folks, you're also speedy. Speedy. About that, did it work?
But I'm already working.
Oh, gee, I don't know how to do that one either. But that means you can't participate. Can you sit closer to somebody so you can see yours? Okay, that looks great. So now you're going to go, you choose the first one. There's A, and then times. Go back in. There, and then choose B, and then enter. Okay, wonderful. All right, so everybody has it. Now, how do we just find an inverse? Like they came right out and told us that these matrices are inverses of each other, meaning if you multiply them, you get the 1, 0, 0, 1. How do we find the inverse of this? So everybody now go back into your matrix, second matrix, and edit matrix A again. It's still a 2 by 2. And go ahead and just put in this matrix right here. So put in 4, negative 3, negative 2, negative 5. And then go to your normal calculator screen where you did matrix A times matrix B. And this time call up matrix A. And once you have matrix A sitting there, you literally just hit the X inverse button. The X to the negative 1 button that you've been pushing to get into the matrix screen. That is the inverse button. It's so important that they made it a button on the calculator. Right? I mean, just think how impressive that is. X squared is a button on the calculator because you square numbers all the time. And X inverse is so important that they made it its own button. So now if you hit A inverse, what do you get?
Bunch of decimals.
You get a whole bunch of really nasty decimals, don't you? That's okay. Let's just go and write it down. So it's important that you know how to do this. So first of all, how many decimals do we need? Yeah, typically we should keep 4 decimals of accuracy. So that would be 0.1923, and below it is negative 0.0769. And then you have to hit your arrow button. So push your arrow button to the right, and it'll take you to the other numbers. Negative 0.1154, I rounded that one. It was 3.8, but I rounded it to 4. And then negative 0.1538. So that matrix is the inverse of that one. Which means if I were to multiply this matrix times that matrix with all the decimals of accuracy, they would multiply it together to equal the 1001 matrix. Did everyone get these numbers?
Yeah.
Okay. Now, it shouldn't always come out to be some nasty decimal. Sometimes it'll come out clean. So let's try that again. Take the inverse of this one. So we hit clear, go back into the matrix, go back to edit matrix A. It's still a 2 by 2. Now make it the matrix 0, 3, 6, 1. And then if you hit second quit, and if you hit second enter, you already have A inverse as a command into your calculator. So if you just hit second enter, it'll pull right back up the fact that you already had A inverse ready to go. And since you've edited this to be your matrix A, you can just hit enter, and it once again gives you a matrix. Now, this matrix, you'll notice, has a lot of decimals, but they're recognizable. What's the first number? 0.05 repeated?
Yeah.
Did everyone else get that? The second number is 0.3 repeating. And then if you hit your arrow to the right, then what? We have 0.16 repeating, and we have 0. Yeah? You didn't? Gee, did I do that wrong? No, that's what I got.
That's what I'm asking.
Okay, well, I'm going to edit 2 by 2, 0, 3, 6, 1. So go back in there and go to edit and then hit enter. 0, 3, 6, 1. Oh, geez. Okay, well, now go back to here, and you're going to hit your matrix A, and then hit exit. Yeah, that's your inverse bus. Did it work, second? 0, 3, 6, 1. You got it. Okay. Now, folks, everybody hit enter. How can you write 0.055555 as a decimal? Well, none of us know off the top of our head, right? Because we don't know those things. But everybody, now go back into your normal calculator screen, hit clear, 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 so it's all gone, and type in -0.0555555555. Lots of fives. You have to go at least to the next line. So fill up a whole row of fives. And then, very special button on your calculator, the math button. You hit math, and then frac, and then hit enter, and it tells you that's the fraction -1/18.
Would you want us to put it in fraction form?
Yes.
Okay.
Yeah. So everybody go ahead and convert the rest of those repeating decimals into fractions. Now the fact is, these numbers up here might also have been fractions, but I didn't see any repetition going on in them, so it wasn't as obvious. And who knows if all those decimals would have given us a fraction. I don't know. But when they're repeating, it's so painfully obvious. It must be a fraction. Everybody knows what 0.3333 is. That's just a third. But 0.1666, I'm not sure. 0.1666666. Sorry, I shouldn't have said it that way. 0.166, and now math, frac. That one was a sixth. And 0. So there we have it. So what are we learning right now? Lots of calculator skills. These are some good, solid calculator skills. And we're almost to the point where we can actually solve a problem, right? Because we're not really solving problems right here. This isn't telling us anything about your business, your profit, or your cost. Right now, we're just learning how to use your calculator. So go ahead and now do number 36. Type that in. So again, second matrix, edit, 2 by 2, and then it's 3, 8, -6, -8. Then I'm going to do matrix A inverse. And once again, now once you get this one, you're going to see -0.333333. Now everybody knows what 0.333333 is. It's a third. So that's going to be -1/3. What's 0.25? A fourth. And then we've got -1/3 again. And then 0.125. Even something as simple as 0.125. I don't know what 0.125 is as a fraction, so I type 0.125, and I hit math frac, and it tells me that it's 1/8. Okay, so how's this working out? Is everyone able to use their calculator to get all these inverses and then convert the decimals into fractions? So did you already see the math frac things? You fill up a whole row, and go math. Frac, and then enter. It turns it into a fraction. You got the math frac? Yep. You down with the math frac? Simone, you're down with the math try?
Yeah.
Host right down with the math try? Is Cheryl down with the math try? Okay, now the last one is a 3 by 3. The great news is this inverse operation we're about to learn works for any size matrix. So there can be 2 equations and 2 variables, 3 equations and 3 variables, and so on. So let's try editing your matrix to be a 3 by 3. So we're going to do 3 by 3, and then it's 2, negative 1, 0, 3, 2, 2, 3, 1. Got it all in there, and then you do a inverse, and you get a nice clean inverse matrix, which is 2, negative 1, 0, 3, negative 2, 0, 5, 4, 1. Now, folks, you'll notice we're not learning how to do an inverse by hand. All right? And that's because doing an inverse by hand is a little tricky. So given a 2 by 2 matrix, A equals A, B, C, D, A inverse is equal to 1 over AD minus BC times the matrix DA negative B negative C. Right? So who wants to do that? It's a very long calculation. You have to take the numbers here, multiply, and then subtract, multiply. That gives you a fraction. And then you change these numbers around, put negatives in front of them, and then multiply that fraction into each number. It's a very long process to do by hand. I don't expect any of you to do it by hand. Plus, this is only the formula for a 2 by 2 matrix. The 3 by 3 formula is, it produces sadness, right? We don't want to do it. Now, for sure, you can go online or in your textbook and look up formulas for calculating an inverse of a 3 by 3 matrix or a 4 by 4 matrix. Your calculator does it for you. Okay, how does everyone feel about finding an inverse? Simone?
So on the test, we don't have to show our work. Oh, kill me.
Yeah, there's just a calculator. So now let's try it. We're going to now go ahead and solve a matrix using the inverse method.
Hi to you.
Oh, yeah, I'm super pumped. I thought you were talking to the whole class. Like while I was facing the board, I thought you stood up, faced everybody.
All
Sorry,
right.
are you excited?
I already knew they were excited.
Oh, yeah. All right. So, folks, here we go. Now, just to get everybody's appetite up, keep in mind, I could just go ahead and write this down as -2, -6, -2, 2, -1, -5, and then I could divide through by -2 up there, and that would give me 1, 3, 1. And then I can divide through by 2 here, that'd be 1, -0.5, and -2.5. And then I can multiply the top row by -1, that'd be -1, -3, and -1, add it into the bottom row, and that would be 1, 3, 1, and that'd be 0, -3.5, and then -3.5. And then I can divide through that bottom row by 3.5, and that would give me simply 0, 1, and 1. And then I could get rid of that 3 by turning it into 0 by multiplying this row by -3. That'd be 0, -3, -3. Add that into the top row, and that would give me 1, 0, -2, and 0, 1, 1. And I'm already done. So there's my solution. This is x, this is y. So x equals -2, and y equals 1, which is the coordinate -2, 1. Right? So I just did that to reactivate your brain, to remind you, what those matrix manipulations look like. And then furthermore, if I wanted to, I could just go into Desmos, right? Like you have a lot of options. I can just go into Desmos. What do you guys think?
Because they both seem to be 6, so I was like,
Because what?
they both seem to be 6.
Oh, you poor things. Yeah, I wouldn't sit there this way.
Yeah, I just thought about it. It's kind of late now.
I know.
And then 2x minus y equals -5. Where do the 2 lines intersect, folks? Is that the solution I got through manipulations?
Yeah.
Yep. Okay, so now everyone's going to be really impressed. Everybody, you're going to be so impressed. Let's do this problem. The way you interpret this problem, first of all, is that this is ax equals b, where a is the coefficients on the variables. -2, -6, 2, and -1. The variable is the matrix xy. And then B are the answers, -2, -5. So first of all, that's just writing down the problem. Now I know it's confusing that this X looks like this X, but this X technically is a 2x2 matrix. So A, sorry, is a 2x2 matrix. This X is really a 2x1 matrix. And this B is actually a 2x1 matrix. So when I write down A, X, and B, these are all three things representing matrices. A is the 2x2 matrix of this, X is the 2x1 matrix of XY, and B is the 2x1 matrix of -2, -5. That's how we interpret this problem. And so the beauty of using this method is we can now say, instead of AX equals B, we can go ahead and say X equals A inverse times B. And that's going to be our solution for X and Y. So X is really the 2x1 matrix, XY. And now everybody, let's type this into our calculator. So what do we have to do? We have to type in the matrix A and the matrix B. Okay, so everybody go ahead and take your calculator and edit in matrix A and edit in matrix B. So edit matrix A is a 2x2 with the entries -2, -6, 2, and -1. And then edit matrix B, which is a 2x1 matrix, 2 rows, 1 column. So 2x1 with the values -2, -5. And at that point, everybody has in matrix A and matrix B. Well, we don't want to multiply A times B. We want to multiply A inverse times B. So when you go back to your main calculator screen now, what you're going to do is call up matrix A, and then you're going to hit the X inverse button, which will make it A inverse. And then you're going to hit your normal multiplication button. And then you're going to go back into your matrix and call up matrix B. And this is what you should see on your calculator screen before hitting enter. And if you hit enter, it gives you the 2x1 matrix -2, 1. Which, again, recall, equals the matrix XY, which are the solutions that we're interested in. So everyone, I just want to walk around the room and see that you've typed in A inverse times B. Oh, okay, yeah, keep it. Yeah, keep editing. Just go over to edit. Wait. Yeah, then are you still editing matrix B? 1, enter. And then you need -2, -5. Then -2. Enter. -5. Enter. Okay, so now you hit second quit, second matrix, and now you're going to do that one, so hit enter. Now hit the inverse button, and then times. And now hit again, second matrix. Choose matrix B. There you go, enter. Boom. Did it work, Sonny? You're almost there? I'll come back. David, did it work? Boom. Diego, did it work? Oh, cool. Adon, did it work? Super. Did it work, please? Nice. Did it work? Okay, I can help you. Did it work? Did it work? Okay, let's see yours. You mean in general about this? Okay, your 2x1 matrix is -2, -5. So right here you type -2, enter, -5, enter. You're always typing a number and hitting enter. So now the matrix is done. Let's check your matrix A. Matrix A was -2, -6, 2, and -1. Very good, you got all that. So now you go back to your normal screen and you do second matrix, choose matrix A, then you hit inverse, then hit times. Then you go back to the matrix and choose matrix B. And then hit enter. Try that all yourself. Okay, well, folks, we did it. We just solved that matrix using the matrix inverse method. Sonny? Oh, well, that's definitely the formula that you're going to do. You still need to edit your matrix because that's a 3x. You need to type in the first matrix, the -2, -6, 2, -1. Yeah, so -2, -6, 2, and -1. So now that matrix is correct. And let's check your matrix B. Edit matrix B. That's a -2, -5. Yeah, you got that. Now this formula will actually work. So I call back up again and enter. And then. Okay, folks. Let's try it again. We're gonna do this one right here. So now we can go ahead and just abstract a little bit. We know that this part is going to be matrix A. We know this part is going to be matrix B. So matrix A is -10, 4, 6, -1. Matrix B is 6 and 2. And what we want to find the answer is simply x equals A inverse times B. So literally, other than identifying the information, it's all done on your calculator. So you got to go back into your matrix, edit the 2 by 2 matrix to be -10, 4, 6, -1. And then edit your matrix B, which is 2 by 1, 6, 2. And then you can go back and you can probably just hit second enter a few times until you get back to the formula you want. And I got the matrix 1, 4. So try that out. Let me know if you also got the matrix 1, 4. Luis, is that what you got? Oh, Dandy. I done? You're almost there.
Yeah, almost there.
Oh, goody, you got it. Oh, goody, you got it. Simon, did that make sense? Oh, you're about to do it. Okay. Yeah, try it out. Make sure it works. Very good.
No, I'm trying to stop. I have like more boxes.
So if you're already done, folks, first of all, how do you feel about this method compared to doing the row manipulations? Oh, I mean, it's way easier, right? Because the calculator is doing it all for you. In fact, what you need to imagine is that somewhere in there, well, no, your calculator's not doing this.
There's tiny little people in the calculator.
Tiny little people, yeah. No, they're doing the method that I just showed you a second ago, that formula for inverses. They're just calculating that formula, multiplying the two matrices together, and you're done. Okay, try one more. And in fact, folks, just do the inverse real quick. Take that, that's A, which is 5, -6, 20, and -24. Just find that inverse real quick. I just want to talk to you about this particular result.
So just find the inverse of that.
Yep, just find the inverse. You don't have to bother typing in the B matrix and multiplying A inverse times B. Just edit in that matrix, that 2 by 2. And then just calculate A inverse.
Ow! Sorry.
What do you get when you, that's correct. What do you get when you hit A inverse?
Error message.
You get an error message?
Singular.
Error message? Error message. You got it too? Yeah, so what does that mean?
Couldn't process it.
It means DNE does not exist. It literally does not have an inverse. Now that's not too surprising. There are some numbers that don't have inverses, such as the multiplication of 0. Let's say I took 10, multiplied it times 0. Can I divide by 0? You can't divide by 0. So as a for instance, 0 does not have a division inverse. You can multiply by 0. You cannot divide by 0. So this matrix does not have an inverse. And why doesn't it? Well, recall I just showed you this formula where if you have the matrix A, B, C, D, then the inverse formula begins by doing 1 over A, D minus B, C. And in that particular case, if I multiply AD times BC, I get, that's negative 120 minus negative 120. And that's the fraction 1 over 0. And you can't divide by 0, and therefore there's no inverse. And so, can you solve this system using inverses? No. So this points out a pro-con relationship of solving matrices with inverses. You might be sitting there saying to yourself, this is how I'm going to solve systems from now on. But the fact is, not every system can be solved in this way. So there is a limitation. Yeah, it's super easy. You type it in your calculator, you're done. But there's a limitation. Now the good news is, this limitation implies something about these equations. What does it imply? That it's not invertible. You cannot find an answer. You cannot find a point of intersection. What does that imply about these lines? They don't intersect. It must mean that the lines are either parallel or it means that they are overlapping. So to an extent then, it actually does solve the problem for you. When you try to get an inverse and it says error, singular matrix, now you know automatically that this system is either parallel or overlapping. So it's not that it doesn't work. It works great. It tells you there's no point of intersection. And so you have to go then and do the further investigation to find out if it's parallel or overlapping. Okay, well that's it. That's the inverse method. Simone?
You probably knew it wouldn't work because you've done it before, but like just how did you know just by looking at it?
I will tell you straight away. What do you multiply 5 to get 20? 4. And what do you multiply by -6 to get to -24?
4.
Therefore, this bottom equation is just this top equation times 4. Up to the other number, right? So if I take that bottom equation, so everyone check this out. If I take that bottom equation and divide through by 4, because I'm allowed to divide through by 4, right? You're allowed to multiply or divide any equation. So the top equation is 5x minus 6y equals -1. The bottom equation, if I divide by 4, becomes 5x minus 6y equals 1.25. Now what does that tell me? This part is identical. This part is different. Had this part been the exact same, what kind of lines would they be? Overlapping or parallel? If they were literally the same line, they're overlapping. And it's painfully obvious. If they're the same equation, it's the same line, so they're overlapping. But since this number is slightly different, and these are the same, but these are different, what does that tell you? It's parallel. So Simone, that's how you know. I looked right here and I said, oh, this stuff is the same. I just have to multiply the top times 4 and I'll get the bottom. Therefore, I know it's either overlapping or parallel. And when I multiply the top by 4, I didn't get -4, so I knew right away that it's parallel. Yeah, good question, Simone. Okay. Now, what's the good news about all this inverse stuff? That you can use this method to solve larger matrices. So here we go. Solve this matrix. We have this whole thing right here. Now, you don't have to write this down, but just imagine. This right here is actually 2x minus 1y plus 3z equals -9. And -3x plus 4y minus 5z equals 9. And this is -4x plus 0y plus 6z equals 4. So this is a system of 3 equations and 3 variables. This would be very challenging to solve. But with your calculator, no problem at all. You just know that you want x equals A inverse B. So everyone, let's go ahead and try it. Just type in your matrix A, type in your matrix B, and then you can do A inverse times B. So, matrix, edit, 3 by 3. Okay. Of course, what's the hardest part about this whole method? Typing it all in? Yeah, I mean, what, is it typing the wrong number? Yes. Yeah, big time. All right, well, when you're all done, I got the answer -95, 11, and 64, which is the answer for x, y, and z. Is that what you got? Oh, you didn't? Well, so what did I do wrong? 3 by 3. 2, -1, 3, -3, 4, -5, 4. Oh, I didn't have a negative sign on my 4. Boy, what are the odds that my typo led to a nice answer? I got a bunch of decimals. It's really unlikely that I got a nice clean answer. Okay, so I got -3.27, -2.10, and -1.517. Is that roughly what everyone else got?
That's what I got.
Okay, great. Okay, well, hey. What that means is that the coordinate of intersection x, y, z, so in three-dimensional space, the coordinate was negative 3.27, negative 2.10, and negative 1.51. Now keep in mind, if you're typing that answer into my math lab, you probably need 4 decimals of accuracy. I just wrote 2 to be quick. You probably need 4 decimals of accuracy.
You want the decimal fraction.
Well, I mean, if these even turn into fractions, I mean, it looks like they end if you type negative 3.275862069 and then hit math frac. It doesn't give me a fraction. In order to use the math frac button, first of all, the decimal has to be long enough to give the calculator enough information to infer which fraction it is. And these fractions or these decimals are not long enough.
Okay, because mine did give me mine.
It did. Well, what do you know? Luis actually did get the fraction. So Luis, in your case, you have the exact answer. In all of our cases, we'll just have a decimal.
We're guessing.
Yeah. All right. Here's our. Oh, now let's see. We have 3 different problems that we can do.
Flip a coin.
Yeah. But everybody, you can cross out number 44 because that's the same as number 43. They're both cable company questions. So we'll do that cable problem and then maybe the cake problem as well. Okay, everyone for number 42?
What about, are we going to do 45 through 7 as well?
I don't see those problems on my PowerPoint.
Kramer's rule?
Oh, yeah, we're going to get to those.
Okay.
All right, folks. Let's do number 44. Now, number 44 is a really good problem because did they give us the matrix? I think you said cross out.
Wait, you said cross out 44.
Oh, sorry. Number 42 is a great problem because they don't give us the matrix. We have to come up with it ourselves. So let's look very closely here. A company makes 3 types of cable. Cable A requires 3 black, 3 white. Cable B requires, cable C requires, and 100 black wires, 110 white wires, and 90 red wires are used. And how many of each cable are made? So, first of all, we have to think, what is our matrix A going to be? And then, what is our matrix B going to be? So matrix B is usually the list of solutions to an equation, like the numbers. Right? Matrix B is normally this part over here, whatever all the variables are equal to. And that's what they told us right here, that they're 100, 110, and 90. So that was our 100, that was our 110, and this was our 90. And what do they represent? This is black, and this is white, and this is red. Furthermore, the row information, so let's look at the size here. This is row by column. The rows are 3 rows by 1 column. The rows represent color. And the column simply represents quantity. Okay. So then what does that tell us about what the size of this matrix has to be? Because in order to even create
A 3 by 3.
this matrix, the A times the X equals the B. Wait a minute.
It's a 3 by 3.
Yeah, it is going to be a 3 by 3 for sure. I was just thinking what the units are going to have to be. Once we, for sure now, since it's 3 by 3, the middle 2 numbers do match. And when we multiply, the result is going to be a what? Since the middle 2 numbers 3 and 3 match, the result is going to be a
3 by 1.
A 3 by 1, which is what we want. However, what we're actually going to multiply is A inverse times B. Inverse matrix, to be able to multiply by this one, this number, okay, what am I about to say? My son will look confusing first. When we multiply A inverse times B, the middle 2 numbers have to match, which means this would have to be the color, because we would need those middle 2 things to represent the same information. But that's of the A inverse matrix, which means the original matrix, you would start with color. And then you'd have the type of cables over here. Boy, I sure hope I'm feeling very confident that I'm saying that right. But this is the way in which we set up our matrix. No, what I just said is incorrect. We can tell because if this is going to add up to that many black wires, then each of these values would have to be a black wire. Oh no, I think that is what I just said. And so this row would have to represent black wires, and this row would have to represent white wires, and that row would have to represent red wires. And therefore, this would be cable A, this would be cable B, and this would be cable C. Okay. Oh, in fact, that is what I just said. That's what it would have to be. Yep. So this represents color and cables. All right. Let's try this out. Now, I kind of helped us out by figuring out where to label these things. Let's just see if it works. What is cable A made up of? 3 black wires, 3 white wires, and 2 red wires. So does that make sense just for column A? We're saying that cable A consists of 3 black, 3 white, and 2 red. All right, so what's cable B made of?
So it's not going to go like sideways, it's going to go straight down. So it's not going to go from left to right, it's going to go from top to bottom, the numbering.
Yeah, well, that's what I'm thinking. I know that on a previous problem we had it the other way.
Yeah.
Right? Yeah. I believe this is correct.
Okay.
So then the cable B is going to be 1 black, 2 white, and 1 red. And then cable C is going to be 2 black, 1 white, and 2 red. Yeah. Now, folks, let's just keep in mind real quick. We just had to make a decision about where to put the row and the column information. Should it be wires over here and cables over here, or should it be cables down here and wires over here? Worst case scenario, what's going to happen? We do it wrong and get the wrong answer. And then we would have to go back and do what?
Switch it.
Just switch it around, right? And honestly, sometimes that's part of the process. Is you try it one way, see if it works, try another way, see if
Are you gonna know if you have the wrong answer on the test?
because the numbers will either work or they won't, right? This is the kind of thing we can actually check. Yeah, so let's go ahead and try it, folks. We have matrix A, we have matrix B, and therefore the solution we're looking for is going to be X equals A inverse times B. So let's try it out. Now everybody just takes your calculator and we type in matrix A, we type in matrix B, and then we do A inverse times B, and we see what we get. Oh, there's 9 o'clock in here. 3, okay. So matrix A is a 3 by 3. There's matrix A. Matrix B is also 3 by 1. Okay.
Oh, that works.
Yeah, it came out really nice and clean, and it came out to be 10, 30, 20. Yeah, this is definitely correct, and it just occurred to me that what would have helped us know which way to put the row in the column would be to do the first step, which we totally skipped. Step 1 is always define your variables. Oh, this will be so much more clear. I got so excited about making my matrices that I didn't define my variables. Okay, so first of all, did everyone get the answers 10, 30, and 20? Okay, now that is correct. Because if let's just say that I had 10 of cable A and 30 of cable B and 20 of cable C, let's just verify the number we got for the number of black. 3. 3. So since I have 10 A cables, so 10 times 3 is 30. So that's how many black wires that I got from cable A. How many black wires do I need for cable B? 1. Just 1. So now 1 times 30. Oh yeah, 30 times 1. That's another 30 total black wires. And then how many black wires do I need inside each cable C? 2. 2. So then that's going to be 20 times 2, which is 40. And if I add all that together, 30 to 30 is 60 plus 40 is 100. That's how many total black wires that I needed, was 100. So that really did work out. Okay. Now, if you all don't mind, I want to erase all that and show you how to start the problem from scratch so you can see how it's not just guesswork. I can tell Josue was really excited about the whole idea, like, oh, if the one way didn't work, just do it the whole other way. Okay, everybody, find some space to do this again with me. We won't write down everything. We won't do the whole problem again. But I'm just going to show you how it is possible to know exactly where to put what. So step 1 is always define your variables, which represents your unknown. So what is the unknown in this question? It says, if 100, 110, 90 were used, then what's our question? How many of each cable was used? Right, so what are we wanting to know? How many of each cable was used? So you begin a problem by saying, let X equal the number of cable A. And then you say, let Y equal the number of cable B. And then you say, let Z equal the number of cable C. How is this helpful? So that we know right up front, because they're asking how many of each cable were made, then obviously our 3 unknowns have to represent how many of each cable, because that's the question they're asking. So now watch how simple this becomes. Since we know that our matrix, the column headers of the matrix are always what? What are the column headers for the matrix? Like back here when we did this problem, the first column is X. The next column was Z. So our variables are the column headers, X, Y, and Z. And what do X, Y, and Z represent?
The number of cables.
Cables. So we know that the top column information is cables. How's that?
Bam. Mind blowing.
Does that make sense now that we know for sure that the cables go on top? And since the cables go on top, what comes over here on this side?
Color.
The color. Has to be. Which in that case is the black, white, and red. So now I have black, white, red. Now you can go about filling all this in. So again, just like we did, cable A is 3, 3, 2. Cable B is 1, 2, 1. And cable C is 2, 1, 2. And then our answer matrix, since each row is the number of black wires, the number of white wires, and the number of red wires, now it makes sense that the 100 black wires goes here. Because the row represents black wires. And so that's the total. And then this row represents white wires, which the total is 110. And this row is the red wires, which the total is 90. And so you can think of this as representing the totals. In fact, row totals. There. So now we have matrix A, now we have matrix B, and you would go about solving the problem using a matrix saying X equals A inverse B. So I apologize for doing that problem the first way, trying to like figure it out as we went. This is the definite way to solve a problem, is to always introduce your variables first. So now that I've said that, let's try the next problem using this technique. Number 43. And remember, step 1 is always define your variables. All right, I can't see it up there. It says, a bakery sells 3 types of cakes, each requiring the amount of ingredients shown. Oh, well, you'll notice they already set up the matrix for us. But look at the question anyway. To fill its orders for the cakes, the bakery used 72 cups of flour, 48 cups of sugar, and 63 eggs. How many cakes of each type were made? So let's try it anyway. What's the question? How many cakes of each type were made? Therefore, that's what we don't know. So we would say, let x equal the number of cake 1. And then let y equal the number of cake 2. And then let z equal the number of cake 3. Okay, I know they already gave us the matrix, but this is a very important technique. You begin a matrix problem like this by first defining your unknowns, by defining your variables. Well, how many of cake 1 did we make? How many of cake 2 did we make? And how many of cake 3 did we make? Now, when we go to make our A matrix, we know these are the variable columns, x, y, z. It must be representing cakes. And therefore, what must the rows represent? In order to fill the orders for cakes, they use cups of flour, cups of sugar, or eggs. So therefore, this is going to be cups of flour. And then this is going to be cups of sugar. And then this is going to be eggs. So everything I just drew right there is how you begin a problem. And you actually start the problem not by filling in numbers, but by labeling your column headings and labeling your row headings. Because now it's just a matter of going in there and typing it all in. Okay, so indeed, that was the matrix they had. 2, 2, 2, 4, 1, 1, and 2, 2, 2. Now let's all work together and see this. What does this first row represent?
Cups of flour.
Cups of flour. How many total cups of flour did they use?
72.
So that's what goes over here. And then the second row represents sugar. And the total was 48. And the third row represents eggs. And the total was 63. So that's our A matrix. That's our B matrix. And to find the solution, you just do x equals A inverse B.
Isn't that 2 supposed to be a 3?
Was in what?
See that column?
Yes, that's a 3. Okay, well, for the sake of time, folks, we're not going to finish that one. Because you can very easily now take your time and plug all that into your calculator and find out what the answer is. We'll go ahead and move forward because there's plenty more matrix problems that we'll see. And as I said, everybody got to cross out number 44, right? All right. All right. Now, what we just did, folks, was one method for solving a matrix with inverses. Would you believe that there's a completely other method for solving matrices with your calculator? Yeah. So on the one hand, we have lots of methods now. We have the manipulation method, right? Where you manipulate the thing row by row until you get the 1, 0, 0, 1. That's one method. We can call that solution by matrix manipulation. We have the second method, which is matrix inverses. And now we have our third method called solve with determinants. Yep. So we have solve with Gauss-Jordan, which is when you want to turn the matrix into this by hand, which you're all very excited about. And that's one method. Solving with inverses, and now we're about to explore a totally different method called determinants. Now, what do you think? Do you think there's any chance that you're going to like determinants more than inverses? Or you're like, I already like inverses. Why are we going to learn something else? Anybody? Any guesses?
I think it might be easier.
Yeah, determinants are actually really great. They're very nice. I would say, is it easier? I don't know. I mean, they're both easy. So now let's learn about a determinant. Okay. I mean, I suppose we could all. We're not taking a break right now. Everyone can just take a deep breath. Actually, didn't we say we would start taking breaks at 3:15?
Whenever, it doesn't matter.
Yeah, whatever, it doesn't matter. It's 3:10. Let's just take a break. That way there's a little bit of a pause between methods. So it's 3:10. Everyone be back in 3:20. Is that a good time for a break?
Yeah.
Might as well.
You said 3:30, right? Or-
No.
No.
Just met it down 3:19.
I tried, guys.
Mr. G,
That's me.
I have to go.
No. Have to is a strong word, Simone. You're saying that literally someone's life depends upon you leaving right now? That
Honestly,
if you don't go, someone could get injured. Simone, you're an adult. If you want to leave, you can leave.
oh, I'm not an adult. I'm.
So I didn't say you're an adult. I said you're an adult. Yeah, so I mean, if you have to leave, that's fine, but make sure you watch the class, because we're about to cover a totally different method and then start chapter 17.
Okay, great, thank you.
Now, Simone, I don't want to make you feel guilty for leaving early,
Uh-huh.
but if I happen to, I'm okay with it. I'm just kidding. So what do I got? Determinant. Oh, man, and just so you know, Simone, literally, we were 2 pages away from being done.
What chapter?
Which was chapter 2.
Yeah, just turn.
And then we'll start chapter 17. I mean, if you wanted to stay, there's literally 2 pages.
I'm gonna watch the video.
Okay, that's fine. I'm just letting you know.
Thank you.
Sure thing.
Almost got it. Mr. King, is that coming? Is that coming?
We should have a copy maker in our room.
Does anybody wants expensive calculator with? You know how to do this. I can return the songs in 1 year. It was very sorry to get that one. What is that video? The plus?
Yeah, guys, I never showed up to school. I got time. The class is so easy, I don't know. You do the test for his class or the alma? I'm just looking at it today. Yeah, I would just copy paste. No, I mean, it looks easy, but then there's like some of them that are like part 1, 2, 3, 4, 5. Where did you go? I mean, which one? Yes. Oh, which one? Already knew here. Did you know that? So, DC sucks.
You're in 7 classes right now?
Technically speaking, it's 6, but I have to pay for 7 because of the way it's split up, the sessions.
Oh, I see. Well, that's intense.
Yeah, because like marketing is considered 2 classes, but it's technically like 1 full semester. It's just split up, or not marketing, economics.
Yeah. Hey, are you going to take that new marketing class they're going to offer?
No, because I have to take a GBS 220.
Yeah.
And
Okay.
it's during the same time.
Oh, same slot, huh?
Well, yeah.
Bummer.
Yeah, the one.
There's a new marketing, like marketing 110 for social media.
Oh, yeah, that sounds really cool.
Yeah, like with me, it's 8 classes, including my second spot.
Like 8 full classes or like split up in the session.
Split up. Right now I'm taking 4, 5. 5.
Okay, we need a couple more people to come back here. I guess just one. Wait, no, Simon and Fred. Come back. And Cheryl. Okay, let's try it, folks. Last method. Then we can start chapter 17. This last method is called a determinant. Determinant. What's another English word that sounds like determinant? Determination, or simply determine. To determine if something has a solution or not. Or use this method to determine the solution. So, how do you calculate the determinant? Here it is. The method, I'm going to write the formula. If you have a matrix, A, B, C, D. Now you'll notice this is a matrix because the bracket turns in. Right, so it kind of goes across, down, and in, and then in, down, and across. So that's a matrix. A determinant, you just use vertical lines. Right? You'll notice these are just vertical lines. They don't have the little bits at the bottom and the top. You see the difference? That looks like a matrix. Whereas now, that's a determinant. So it's just a vertical line. Determinant of a matrix A, B, C, D is simply the value AB minus BC. Very simple computation. You multiply A times D, and then you subtract B times C. It looks like a diagonal pattern. Because when you multiply, let me show you. When you multiply A times D, that's this diagonal, so you multiply A times D. And then you multiply B times C, and you subtract the two products. So what is it? You're slashing to the right, and then slashing to the left. So you go slash right, slash left, and you subtract. So let's try it. We'd like to find the determinant of 8529. So we're going to first slash right. So 8 times 9, the determinant will be 8 times 9, minus, now slash left, 5 times 2.
We've done this before.
You probably have. So that's 72 minus 10, which is 62. Now, what does the 62 represent? That's a totally different class. So we could talk about it, but the fact is the determinant itself does represent something about two-dimensional space. And I suppose I could just go ahead and tell you real quickly. Like, let's say that I had a graph of a square. Okay, and my square is a 1 by 1 square, and therefore the area is 1 times 1, which is 1. So there's my 1 by 1 square. And then let's say that I did a transformation to make the square bigger, okay, but also slanted. So like on the one hand, I could transform this to slide the top line over to here and then still connect it to look like that. Well, that transformation right there, the area actually stays the same. The area of the tilted square is actually the same as the original square. So I haven't actually changed the area at all. But let's say that I move the top and I move it upward and say I move it over to here. Then what I've done is I've really grown and stretched the amount of area. No, am I saying this right? I don't want to tell you the wrong thing. But the fact is we're going to do some sort of transformation to make this object much bigger. And in that case, you might be wondering, how many times bigger is the area? And that's actually what the determinant tells you. is how many times bigger is the area of the original shape compared to the second shape. Now you might say, when on earth did we start talking about shapes? I thought we were talking about systems of equations like 2x plus 3y equals 5 and negative 2x minus 8y equals 13. Well, we are talking about systems of equations, but the determinant can also be used to represent other things. And so this number represents a multiplicative factor of how much bigger the areas get. Okay, so that said, we'll find another determinant. We don't need to know that interpretation. It's enough just to know it's a number and it's not 0. So let's try again. Our determinant will be multiplied to the right. So that's -1 times -3 minus multiplied to the right. That's -2 times 1. You'll notice how I'm using parentheses. We're about to subtract these two numbers, so it's really important that you don't get the sign wrong. So then what is this? -1 times -3 is 3, minus -2 times 1 is -2. That's a double negative. Chop, chop, that's 5. We'll try this one more time. This determinant be multiplied to the right, so that's -1 times 3. And then subtract, multiply to the right, sorry, to the left, and that's 1 times 3. And now what do we get? That's -3 minus 3, which is -6. In each of these cases, you'll notice that you got an actual number not equal to 0. And that's the first lesson, is that in order to use determinants to solve a matrix, the determinant does have to equal something other than 0. If it equals 0, that's like a inverse of a matrix that implies the lines were either parallel or overlapping. If you get a determinant of 0, that actually implies that the lines are parallel or overlapping. Okay, now let's try that on your calculators, folks. This computation is easy enough that you can do it by hand, but your calculator can also do it for you. So let's try that first one on your calculator.
Power of technology.
That's wonderful. So everybody go ahead and edit matrix A to become a 2 by 2 matrix. And type in this first matrix, 8, 5, 2, 9. There we go. And then go back to your main calculator screen, hit second matrix. We're going to type matrix A. Now we need to be able to tell it to do the determinant of that. So where's that information? If you go into second matrix, the first column says names, math, edit. We're going to go into math. And if you go over to math, what's the very first option? DET, which is determinant. And I'm sorry, it's determinant of parenthesis, which means you have to type determinant first, not A. So you have to do second matrix, math, determinant, and then go back, second matrix, matrix A. And what you'll have on your screen then, it should say determinant, parenthesis, matrix A. And then whether you put a parenthesis or not, it's still going to give it to you. And what do you get? 62. 62. So do you have to do the determinant by hand? No. You can just use a calculator. Can you do the determinant by hand? Yes, you can. It's easy enough that you can do this by hand. The inverse was not nearly so easy to do by hand, so we just used calculator. This one, if you wanted to, you could just do it by hand. So here's the exciting thing. Here's our last solution, which is wonderful. It's clever. It's lovely. It's elegant. Something you tattoo on your back.
Get a nice piece.
Exactly. So here we go. We'd like to solve this solution. This is called Kramer's rule. Okay? So first of all, everybody, if you have another color writing tool, like a blue pen or something, that'd be great. First, let's go ahead and get matrix A. So here's matrix A. And then this is your matrix B. And if you did just call that A and B, you'll notice you could just solve this using inverses. So, I mean, we could just solve it by inverses, but we're not going to. Instead, we're going to first compute the regular determinant, which is using the regular numbers from the coefficients on the variables x and y. So we're going to put in 1, -3, -3, -4. That's your regular determinant using the coefficients that are on the variables x and y. Now watch what we're going to do. Next, we're going to create a different determinant, and we're going to call it d sub x. That's a subscript. Kind of like, subscripts like x sub 0, x sub 1, x sub 2. That's a subscript, d sub x. And what we're going to do is replace the coefficients in the x column. We're going to replace the coefficients in the x column with the solutions, 21 and 15. And that is what we're going to call determinant x. Determinant x, or d sub x, is the coefficient you get if you replace the first column with the solutions. You're replacing the x coefficients with the solutions, 21, 15. Next, we're going to create a determinant called d sub y. Same thing, we're going to replace the y coefficients with the solutions, which means you keep the original x coefficients, but you replace the y coefficients with the solutions. So, is that fair? In the original matrix, or determinant D, you keep both. In D sub x, you replace x and keep the y. In D sub y, you replace the y and keep the x. Okay, now we're going to go ahead and calculate those determinants. And honestly, in my opinion, the amount of time it takes to type all that into your calculator, might as well do it by hand. All right, to calculate these determinants. So remember, if you want to have the formula on the top of the page, determinant of A, B, C, D is AD minus BC, where you don't even need your calculator at all. You can do all these computations in your head. That is provided that the systems are easy now. So we do a right multiplication and then left multiplication. So let's go about starting to solve these determinants, and then you'll get to see where we're going with this. So right multiply, that's 1 times negative multiply, negative 3 times negative 3. So what does that give us? Negative 4 minus 9, which is negative 13. So that's the original determinant regarding the coefficients of the original x and y variables in the system. Now let's do determinant sub x. Again, we'll do our right multiplication. So that's 21 times negative 4 minus our left multiplication, 15 times negative 3. And that gives us negative 84 minus negative 45. You can see I have a lot of positives and negatives going on here. You have to be very careful. We have a double negative, which is a chop chop. And negative 84 plus 45 is what?
Negative 39.
Yeah, negative 39. All right, now we'll finally calculate our last determinant. So again, we do our right multiplication, so that's 1 times 15, minus our left multiplication, it's 21 times negative 3. And that gives us 15 minus negative 63. That's a double negative, so that's chop chop. 63 plus 15, so 78. Now I showed you how to do all the computations first. Now I'm going to tell you what Cramer's rule is, because that's what the instructions up there say. Use Cramer's rule. Cramer's rule is beautiful. The solution to the system of linear equations, x, y, is determinant x divided by determinant y divided by determinant. That's actually the formula. That tells you the point of intersection. It just tells you the point of intersection. So in our case, d sub x is negative 39, d is negative 13, d sub y is 78, and d is still negative 13. And you simplify those fractions and you get 3, comma, negative 6. That's it. That's the point of intersection of those two systems. Had you taken the time to graph them and looked, the point of intersection would be at 3, -6. If you plug in the numbers 3, -6 in for x and y, it'll make both equations true. If you solved it with the inverse, you'd still get the answer 3, -6. If you solved it with manipulations, you'd still get the answer 3, -6. What do you think of Cramer's rule, which boils down to this formula right here? What do you think of that? The point of intersection xy is the determinant d sub x over d, comma, d sub y over d. Anyone like that method? Who said that? Josue? You don't like it? What about it don't you like?
Takes longer.
It does take longer. I have to admit the inverse method is probably the fastest. Okay, now the nice thing about the determinant method, just like the inverse method, is that it doesn't just have to be 2 by 2. You can do this with a 3 by 3 matrix, a 4 by 4 matrix. It completely allows you to solve any system with no matter how many equations or variables that you have. Again, this is only if determinant is not equal to 0. Because for instance, what if d equals 0? Then you'd have something divided by 0, which is undefined. And so there would be no solution. So in order to use this methodology, you just need to know, provided d is not equal to 0. Keep in mind, d sub x and d sub y can equal 0. D sub x and d sub y can be 0 because you could have 0 divided by 5 is just 0, and that's just that part of the coordinate. So d can't be 0, even though d sub x and d sub y could be anything, including 0. All right, everybody, we're done with chapter 2. Michelle, what? You are correct. I did not do 2.1, nor will we ever.
Okay, so it's not on the board.
I think I took it off the homework, and if I didn't yet, I will. Here, let me make myself a note. Remove 2.1.
I don't want to do that.
Well, I'll tell you, Josue. Everyone, Josue asked a good question. Why don't I want to do that one? I don't think it's necessarily personal. I mean, I guess it is personal. Like, I don't want to do it. The fact is, the method that they teach is worse. These are the good methods. Like the Gauss-Jordan thing, that inversely determines. These are good methods. The method from lesson 2.1 is not quite as good as Gauss-Jordan, and you end up having to do a lot of substitution. So section 2.2 Gauss-Jordan is an improvement upon section 2.1. They really just introduce you to 2.1 to kind of put the idea in your head, and then they really refine the idea of Gauss-Jordan. No one in the world solves solutions with 2.1. Nobody. Only Gauss-Jordan is what's used. Did that answer your question, Respect? Okay, great question. Thanks for asking it. Everyone, we're not going to do section 2.1. It won't be on your homework, and it's not on the test. I already took it off the test. I might just have to go take it off my math.
What about 15?
Yeah, I think I'll, well, no. Yeah, I mean, 15 and 16, if you look, that's just examples of solving systems. All of you can do that now with inverses. So 15 and 16 is fair game. It's just a 3 by 3 matrix and you solve it with your calculator. Thanks for asking me, Cheryl. All right, everybody. Well, gee whiz, we're about to start chapter 17. I feel like I should give you another break, but I'm not going to. All right. So chapter 17 is very different. Like, we just spent chapter 1 talking about solving linear equations in point slope form, and then we spent chapter 2 talking about solving systems with various methods. Chapter 17, now first of all, you might say, oh my gosh, Mr. G, we just went from chapter 1 and chapter 2 all the way up to 17. But believe it or not, it's the natural place to put this material because it's going to be matrix methods. So at the beginning of chapter 17, we're just doing derivatives. It's calculus all over again. We're just going to do some derivatives. And then by the time we get to the end of chapter 17, we do derivatives and we use matrix methods, which we just learned. Nice. Yeah, exactly. Nice. So, would anyone like to ask any questions or say anything before we start? Okay, well, I don't really said anything, so I guess it's a no. All right, well, let's begin. Chapter 7, now by the way, go ahead and take your pen up there and say section 17.1. I have a little typo there. Section 17.1, multivariable functions. Now this is really exciting. Normally a function is just a function in one variable. So like f of x equals x squared minus 3x plus 7. We call that a single variable function. We normally don't even bother calling it a single variable function. We just call it a function. Whereas now we're going to do multivariable functions. Take a look at this. Now isn't that fun? That means we're looking at a function that depends on two things, right? And I'll give a really good example. Weight maintenance has many variables, but let's just say that two variables are calories eaten and exercise performed. Right? So I mean, if you want to lose weight or maintain your weight, you need to, be eating the appropriate amount of calories, not too many, not too few, and you need to do some exercise. And on any given day, if you want to eat an extra 500 calories, maybe there's a slice of pizza that looks really good, then you'd have to do a little bit of extra exercise, right? At least that's common thought, right? It's what?
The basics.
It is the basics. And you hear people say it all the time, like, oh, I had that slice of chocolate cake, I'm going to go have to run an extra half hour on the treadmill or something like that. People say these things. Okay, so that would be a multivariable function right there. You could define a function instead of f of x, now it's f of x comma y, and you'd have some sort of function here that would allow you to compute whether or not you're keeping your weight the same, gaining weight, or losing weight. I don't know what that function is, I'm just giving it as an example. So here's a multivariable function right here. And with this function, not only can you plug in numbers for x, but you can plug in numbers for y. So let's just try it. We have this multivariable function. You know how I like to write functions empty. So f of xy is equal to 9x plus 4y minus 5. And now you actually have to pay attention to what goes where. So they said find f of 7 comma negative 8. So 7 is your x, negative 8 is your y. So we have to be careful now and really watch what we're doing. 9x. So right here I'm going to put my x, which is 7. And this is 4y. So right here I'm going to put my y, which is negative 8. And so f of xy is equal to 63 minus 32 minus 5, which is what? 31 minus 5? 26? Did anyone else get 26? So that's called a multivariable function. Now right away, you might ask, what does that look like? What does that look like? And right up at the top of your page, now first of all, Desmos, I don't think they have a two variable function graph. Or like if I do 9x plus 4y, I don't think they even know what to do with it. Look what they do. A little exclamation point. They're like, what is that? So instead, there's a great website you can go to called GeoGebra 3D. GeoGebra 3D. Do you see that written at the top of your page?
Yeah.
Yeah, so GeoGebra, what is that? Geometry, algebra. GeoGebra. Geometry, algebra, GeoGebra. So here's GeoGebra, and I'm going to go into the 3D graphing tool for GeoGebra. And when you go home tonight, I'm sure you'll all want to go here and see this. And now I can type in 9x plus 4y minus 5. And there is a three-dimensional graph of what 9x plus 4y minus 5 is equal to. Yep. And so that plane, that three-dimensional plane there, every possible value that I can plug in for x and y is going to be on there somewhere. I wish I could actually show you the example. So a of -7, 8. First of all, they must not be looking at the same thing we're looking at. Oh, that's because I have my signs wrong. 7, -8. There we go. They also got the answer 26. Okay, well that's not very exciting because it's just one big flat sheet, right? Okay, well, let's go try the next one. What's this next one gonna be? It says g of -6, 3 when g of xy is 6y squared minus 3xy. So again, we have this multivariable function. What does it represent? I don't know. It could represent profits, where maybe x is the number of units we sell, and y is the number of employees we use to do it. All right, so for every unit you sell, your profits are going up, but if you use lots of employees instead of just 3 employees, you're spending a lot more money to get the work done. Okay, so let's try that one. So g of xy, and we're going to plug in -6 and 3. -6 and 3. So again, write it empty. 6 blank squared minus 3 blank blank. So there's our multivariable function. We're going to plug it. Again, you have to be so careful. This is 6y squared. So this is where we need to put y, which is 3. And then x, that's -6. And then this is a y, so that's another 3. So you really have to use your fingers to point back and forth and see what all you're typing in. So what do we have then? 3 squared is 9, 9 times 6 is 54. And then -3 times -6 is positive 54. And so that's 54 plus 54, which is 108. Did anyone else get 108? Okay. Well, that's pretty basic. Now let's look at what that graph looks like. 6y squared minus 3xy. I'm going to go back in here. We're going to type in 6y squared minus 3xy. Ooh. Now spend some time looking at this. What does this graph look like? Have you ever seen anything like it? No. So on the one hand, that right there looks like an upside down parabola. But if I turn this way and look, it looks like a right side up parabola. And if you look at it, one thing you could say that it looks like is a pair of pants you're about to step into. Do you see what I'm saying? Is that a pair of pants you're about to step into? This is the crotch, for lack of a better word for it. And right, I mean, could that be a three-dimensional model for a pair of jeans? Anybody? Yeah? Okay, well, so there we go. That's what the graph looks like.
Jeans.
Yep, a pair of jeans. So obviously this graph continues on infinitely far in both directions. Okay, but that's the space of solutions for that particular multivariable function. Okay, well that's all there is to say about that. So what's our next question? This thing. So just look at the wide variety of things that we can graph using a multivariable function. So now let's just play around a little bit. First of all, they told me to go ahead and use that formula, which is what? X squared plus y squared plus z minus 1 squared, and all that equals 1. There we go. So what is it? It's a sphere. It's a little sphere. Look at it. It's sitting on the table. I mean, it's just a ball that's sitting on a tabletop, essentially. Now, the graph is just a sphere. So that's a sphere. So which one of those options is correct?
D.
Yeah, it looks like D. Although I admit A and D both look a lot like each other. They're both a sphere that's not minus 1 and z minus 0. The sphere is now centered at the origin. But by putting the z minus 1, I shifted the sphere along the z-axis, and I moved it up. Watch, I could also put z minus 3, and it will shift the whole sphere up. Okay, so there's a lot of things that you can do with graphs. So this is one potential graph. Now let's see, what if we just play around with this a little bit? What if I change the z term, and I don't square it? Oh, that says it's undefined. Okay, apparently I broke it. What if I just make the z? There we go. What's that? Oh, there we go. Look at this fun thing.
Volcano.
Yeah, it looks like it could be a volcano. What is it? Yeah, it's what two-dimensional shape does it look like?
A cone.
Yeah, it looks like a parabola. A cone would be perfectly straight, you know, like a dunce cap. But this is like a parabola, but a three-dimensional parabola. That's kind of fun. Yep, so there's that equation. That wasn't on our list. What if we give the equation, oh gosh. I don't know how to make some of these. We'll just do x squared plus y squared. Oh, okay, now that's facing up. Then we'll do equals 2. Oops. Squared equals 2. Oh, there we go. Oh, look. Let me delete that first one. There we go. Now what is this?
Silencer.
Okay, yeah, it could be a toilet paper tube, but sure, a silencer. So there we go. We have a just a big tall cylinder, right? Okay, well, I mean, you can see. Obviously, you can spend hours playing on this website, right? You're all gonna go home tonight,
Yeah.
and you're just gonna start typing in variables until you start making things. And obviously, any equation you can type in with 3 variables or even 2 variables is going to produce a unique 3-dimensional shape. So now we'll go back to this one. What's one question we could ask about this paraboloid? It's called a paraboloid. What might you want to know? What part of the paraboloid is that part right there? What? Think about calculus. What we're always finding about curves. We're trying to find the. In calculus, we were constantly taking a function and finding the. Yeah, the min-max. You're trying to find the maximum and the minimum, right? So in calculus, we did single variable functions and we found minimums and maximums by taking the derivative, setting it equal to 0, and that found you your critical points or your flat spots. Whereas now in multivariable functions, you can find the maximum of a 3D graph, which is pretty exciting. I know you're all really excited. That's what we're doing in chapter 17. In chapter 17, we're going to take multivariable functions and find the maximums and the minimums. So for instance, just take a look here at your graph. Let's just conceptually talk about it. Where's the maximum of this sphere? Right up here? Label it in, folks. There's your max. Where's the min?
At the bottom.
And at the bottom. So you have a max and a min. What about this cone-shapy thing? What's the maximum? Yeah, I mean, it keeps going forever, right? So like, if I were to show you a parabola and I said, where's the maximum? Is there a maximum? No, it just keeps going up forever. So this thing doesn't have a maximum. Where's the minimum? At the bottom. So there's your min. And then what about this cylinder object? Again, theoretically, it goes up forever and it goes down forever. Is there a maximum? No. No. Is there a minimum? No. How about the sphere? Max, min. Okay. So by introducing the idea of a multivariable function, we now have 3-dimensional shapes instead of just 2-dimensional shapes. And we're still able to use calculus to find the maximum and the minimum, such as the maximum profit or the minimum cost, and so on. The only difference now is that the fact that it's a 3D shape is allowing us to have more than one variable, right? Because a business consists of more than one variable. Let's say that your business is farming. One variable is how large your land is. Another variable is how much rain you've gotten. Another variable is how much sunshine you've gotten. Another variable is how many employees you have working the land. Another variable is how many insects and pests are ruining your crop. Another variable, and so on and so forth. So there are lots of variables that go into business problems. And by making multivariable functions, we're now looking at very complex 3-dimensional graphs, which fortunately, we can still find the maximum and the minimum of. And therefore, you know, find maximum profits and minimize cost. Now, I said here to do an interlude. Did I give you folks this page? I don't think I did. Where did I go? I guess I didn't print it, or I did. Here's what I need everyone to do. Take out a sheet of lined paper, and we're just going to review some basic calculus. Everyone take out a sheet of lined paper. And let's review some basic calculus. Joe, you can do it on that. Bunta just asked a great question. Can you just put your calculus review on the very back of your packet? Sure, because then it's right there with it. Okay, so the primary type of derivative we'll be doing is the power rule. For some of you, this is fresh. For some of you, this was a semester ago. The power rule states that if your function is f of x equals x to the n, then what's the derivative? Yeah, that's it. You multiply by the n, you multiply by the exponent, and then you subtract 1 from the exponent. So as a for instance, if you had f of x equals x squared, then the derivative would be you multiply by the 2, and then subtract 1 from the exponent, it'd be 2x to the 1. Now, there's a couple of special cases we need to remember. What if it was just f of x equals 5x? Yes, just 5. Maybe you all remember that. That if it's just a single variable, then it's just the coefficient out in front. So it's just 5. And the way you remember that is by actually putting 5x to the 1. Because then you multiply by the 1, so 5 times 1 is just 5. And then if you subtract 1, that's 1 minus 1 is 0, and x to the 0 is equal to?
0.
No, not 0.
Oh,
1. Yeah. So normal power rule, the derivative of a linear term, so the derivative of 5x is just 5. And then another special case, what if the function was f of x equals 8? What's the derivative of a number? Derivative of a number is?
0.
Just 0. And again, you can convince yourself of that because 8 is actually 8x to the 0. And therefore, you multiply by the 0. 8 times 0 is 0. Subtract 1 from, well, you can subtract 1 from the exponent and you'll get x to the negative 1, but 0 times anything is still 0. So the answer is 0 either way. Okay, so those are some important, simple cases of derivatives that we need to know. So now I'm going to go ahead and call on all of you and ask for some answers. So, what is the derivative of 4x plus 1? I will start with Diego. The derivative of 4x?
4.
And the derivative of 1?
0.
Yeah, so it's just 4. David, what's the derivative of 2x?
2.
And the derivative of 1?
0.
Yeah, just that's it. Okay, these a little more complex here. Bata, the derivative of 5x squared.
1.
Yeah, 10x to the 1. And what's the derivative of negative 2?
Yeah.
0. So it's just 10x. Sadi? Yeah, just 6x, because the 1 goes away. Very good. And let's keep going. How about Sadia? What's the derivative of 5x squared? Yeah, just 10x. And then there you go. Okay, so Adon, what's the derivative of 5x cubed?
15x squared.
Yeah, very good. And then Luis, the derivative of 5x?
Just 5.
Yeah, just 5. And Michelle, the derivative of 3x?
3.
Yeah, just 3. And Josue, the derivative of 3?
0.
Yeah, just 0. Same thing, the derivative of 5 is just 0. Okay. So those are some basic ones. I said skip all that because we don't need it. Chain rule. I think we might need to remember the chain rule. How does the chain rule work? I'll verbalize it for you. When you do the chain rule, you take derivative of the outside, leaving the inside alone, and then what?
Or times the
Yeah, then multiply by the derivative of the inside. Okay, so let's try that real quick. I've got my function 3x equals 1 all to the 4th. So my derivative is going to be, take the derivative of the outside, so that'd be 4 to the 3rd. So I multiplied by 4, subtracted 1, leave the inside alone, and then multiply by the derivative of the inside, which will be 9x squared. How's that for everybody? All of you who just took calculus, that's probably just an easy review. Just to Don and Luis, it's been a month or a semester for you guys, so there you go, that's the chain rule. So Adon, for fun, you get to try this next one.
So it'd be
Derivative of the outside first.
so 5 to the 4th,
Yeah, 5 to the 4th.
and then 8 to the 3rd, x to the 3rd.
Yeah. Yeah. Okay, very good. So that's the chain rule. I don't think we have to do the product rule. We might have to do the product rule. So let's do a product rule, shall we? Let's say that you have a product rule, and I'm going to write this down here up higher so everyone can see it. So f of x equals 2x to the fourth plus 2 times x to the fifth plus 4. So product rule. If you recall, the product rule states you take the derivative of the first times the second plus the derivative of the second times the first. And so the way we write that down is by just giving yourself 2 parentheses plus 2 parentheses. That's the structure of the product rule. And you do the derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first is simply 8x cubed times the second, which is still x to the fifth plus 4, plus the derivative of the second, which is 5x to the 4, times the first, which is still 2x to the 4 plus 2. All right, so that's just the structure of the product rule. We would still have to simplify all that, right? We would still have to simplify all of that, which isn't too bad because you just distribute and you distribute. So if I were to distribute that, that'd be 8x to the 8th plus 32x cubed. And then next, I would have 10x to the 8th plus 10x to the 4th. And now that I've distributed, I can also combine my terms. I have multiple x to the 8th terms. So it'd be 18x to the 8th plus 10x to the 4th, and then plus 32x cubed, putting my terms in downward powers of x. So I do my x to the 8th, then x to the 4th, then x to the 3rd. Okay. This probably feels like a fast review because it really is. I'm just kind of activating your memory about these things that you've done in the past with the power rule, the chain rule, and the product rule. I don't think we have any quotient rules that we have to do. So we'll certainly take our time as we solve the problems that we actually see in section. This was just a review of main calculus ideas you've seen in the past. Yeah. So probably what you want somewhere on your page, and I'll go ahead and do it right here, is a reminder of our basic rules. So f of x is x to the n. That gives us the derivative is nx to the n minus 1. And if f of x is equal to mx, and the reason I use mx is because that's mx plus b, a linear equation, then the derivative is simply m. And then if I have f of x is a constant term, then the derivative is simply 0. And then we also have the product rule, and we have the chain rule. Okay, so that's all the fundamental calculus you need to remember from before. And again, that's just to kind of spark your memory, because now we will proceed to do some more advanced stuff. Okay, everybody ready? All right. Boy, it always just cuts off my instructions. It says, find the difference quotient of the multivariable function. Now, first of all, before we do a difference quotient of the multivariable function, let's all remind ourselves how to do the difference quotient of a normal function. So remember this, if I have a simple parabola, f of x equals x squared, or my graph looks like this, and remember we had this thing called the difference quotient where f prime of x was equal to the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x, which simplified to just f of x plus h minus f of x all over h. Who remembers that? I mean, I hope all of you. That was called the difference quotient. And this was the definition of how to take a derivative without using any fun rules, like the power rule. Okay? So let's demonstrate how to do that with just an x squared term. I would write this down. Everybody, I would write this down. Because what we're about to do is harder than this. So you, at the very least, want to be able to do this. So we're going to use this definition, which is the difference quotient, and we'll use a simple function f of x equals x squared. So what do? What does f of x plus h mean? We plug x plus h into, which is x squared. So our difference quotient, I'm going to start it off by just writing it, f of x plus h minus f of x all over h. So f of x plus h means plug x plus h into the function x squared, so that gives us x plus h squared. And then we'll subtract f of x. That just means plug x into our function, which is literally just x squared, so there's x squared, all over h. You don't remember it yet, you will in just a moment when we finish solving the problem. Now, how do we expand x plus h squared? What is x plus h squared? How do you solve x plus, or how do you simplify x plus h squared? That's really x plus h times x plus h. And so you have to do FOIL. So x times x is x squared. X times h is hx. X times x is hx, and then h plus h, or h times h is h squared. And then you can combine like terms, and we get x squared plus 2hx plus h squared. So that's just what x plus h squared is. So now I can put that into my quotient here. X squared plus 2hx plus h squared minus the x squared. Okay, so I'm done with the binomial now, minus the x squared. And what happens? What happens in the numerator?
X squares cancel out.
Yeah, x squareds cancel out. Now we just have 2hx plus h squared all over h. Now what do we do in the numerator? Yeah, we can take out an h. So now we just have 2x plus h all over h. And what happens to the h on top and bottom? Yeah, these h's cancel, right? And so we're just left with 2x plus h. Now, what were we doing from the very beginning? We were taking the limit as h approaches 0. So what happens when h becomes 0? What are we left with? Just 2x. And you'll all recognize that. That's the derivative of the original function, x squared, which we all know from the power rule. What's the derivative of x squared? 2x. Because right here in the very last thing you do is you let h equal 0. So this whole process that I just walked you through is doing the difference quotient for a simple single variable function. Remember that, David? Okay. John and Luis, I know that's been a while for you too.
It's clicking.
It's clicking. The key is that they give us a definition to follow. And we just plug everything in, do a lot of advanced techniques for algebraic manipulation, we get our answer at the end. But for sure, you all recognize that the derivative of x squared is 2x, right? Because you multiply by the power and then subtract 1 from the power. So what does the difference quotient do? It finds the derivative. So let's put that in our note. It says, find the difference quotient for the multivariable function. The difference quotient, what does it do? Finds the derivative. Okay. Well, I can tell you right now that you're all going to love this. You're going to say, oh my goodness, Mr. G, this is wonderful. I'm so glad that I'm here today, that I get to experience this. Now, first of all, does this look like the difference quotient that we just did? It says limit as h approaches 0. There's the f of x plus h, but there's a y next to it. And then minus f of x, but there's a y next to it. So we're still doing, fundamentally, f of x plus h and f of x. It's just that it's a multivariable function, so the y comes along for the ride. So let's try it. We're going to have something minus something. That's fundamentally what is happening up there. You've got f of x plus h comma y minus f of x comma y. So what do we write down first? We're going to plug x plus h in everywhere you see an x. So what does that give us then? We're using this expression. It's going to be 10x plus h minus 6y squared minus 4. And then minus just regular old f of x comma y, which is just the function itself. So minus 10x minus 6y squared minus 4. All over h. Okay, so now we just have a algebra. So up top, I'm going to distribute my 10. Now I have 10x plus 10h minus 6y squared minus 4. Now look, we're distributing a minus. So that's going to be minus 10x minus negative 6y squared, that's plus 6y squared, minus negative 4, that's plus 4. All over h. Now remember, in calculus, you do lots and lots of algebra, but tons of things cancel out, right? That's always what happens when you do algebra properly in calculus. Almost everything cancels out. So what cancels out? Yeah, the 10x's cancel out. The 6y squareds cancel out. Even the 4's cancel out. Now what are we left with? 10h over h. And then the h's cancel out, and we're left with 10. Now this tells us something really interesting, okay? Wait, why are you smiling, Josue? Because it's so silly at the end?
No, because I didn't believe you that it was going to be like this.
Oh, okay. I try not to lie, Josue. Okay, so what did we just find out? Let's take a look here. See, if we had just done f of x equals 10x minus 4, okay? I stripped away the part that has a y in it. Let's pretend it was just f of x equals 10x minus 4, right? What would the derivative have been? 2. It was 10, right? Same answer we got. So what we just learned was, if you have a multivariable function, so in this case it's 10x minus 6y squared minus 4, you can choose which variable to take the derivative with respect to. So like, let's say that I want to take the derivative of this function with respect to the variable x. Okay, so let's try that. With respect, that's the phrase, with respect to x. Now that sounds like with respect to my homies or something, like, what do you do, like with respect? I don't mean that. I mean with respect to the variable x. So what I'm going to say is, only the x variable is a variable, everything else is a constant, right? So 10x, that's a variable term. If I want to take the derivative of that, it would indeed be 10. But now I'm saying 6y squared is just a constant. This requires a little bit of imagination. I'm saying just pretend 6y squared is a constant, like 30. What's the derivative of 30? 0. And so if I'm telling you 6y squared is a constant, then what's the derivative of 6y squared? 0. Right, this takes a little bit of active imagination. We're only treating x as a variable. Everything else is being treated as a constant. So the derivative of 10x becomes 10. The derivative of 6y squared is just a number, so that's 0. The derivative of 4 is just a number, so that's 0. So now how do we write this down? Instead of continuing to write, so now what we do is, instead of primes, okay, so I'm going to write this down, but it's not correct. We don't write f prime of xy anymore, because prime implies derivative, but you need to choose with respect to which variable. And we did it with respect to the x variable. So we would say f sub x of xy. And that means the derivative of this function with respect to variable x is simply 10. Because you treat only x as a variable and everything else you treat as a constant. So let's try this again. What if I want to take the derivative of this function with respect to y. So I'm only going to treat y as a variable, and everywhere you see x, it's just a constant. So let's try that. Everyone write down f sub y of x comma y. What would our derivative be
12.
if we only treat y as a variable? First of all, we can take this variable or this derivative pretty quickly because we're saying, okay, y is a variable. So this would be what? Negative 12y? Right? The derivative of just that part is negative 12y. Well, what's the derivative of negative 4?
0.
Still 0. And what's the derivative of 10x?
0.
0, because we're pretending that x is a constant. So there we go. This is f sub x of x comma y. This is the derivative with respect to x. The answer is just 10. And here, the derivative with respect to y, the answer is just negative 12y. So the fact is, even though we just sat here and we did the difference quotient, we don't have to keep doing that. The difference quotient told us something really interesting, that if you do the difference quotient with respect to x, you know, we did x plus h. We didn't do y plus h. We did x plus h. So it means we were doing the derivative with respect to x. You take the derivative, treating x as a variable, and all the y variables are just considered constants. This is brand new. Okay, this takes a little bit of time to wrap your mind around. So let's go ahead and try this next function. We don't have to do the difference quotient. You can cross that out. But let's just talk about taking the derivative with respect to each variable. So first, sometimes it's helpful just to write the function down in your own writing. F of x comma y equal 4x minus 7y squared minus 7. So the first thing I'd like to do is take the derivative with respect to x. So that f sub x means I'm taking the derivative with respect to x, which means I'm treating x as a variable, everything else is a constant. Yeah, so the derivative of 4x is 4, 7y squared is a number, the derivative of a number is 0, 7 is a number, the derivative of a number is 0. So the answer is 4. Then we can take the derivative with respect to y. And so, okay, with respect to y is a variable, everything else is just a number. So if I take the derivative with respect to y, this term, for sure, I have to find a derivative. So that's going to be negative 14y. But x is just a constant, so this derivative of a constant is 0. And 7 is a constant, derivative of a constant is 0. So there we go. Now, I just told you a rule for taking the derivative of a multivariable function. And that was that when you have a multivariable function, there's no such thing as the derivative. Like you wouldn't write down f prime of x comma y, because you have to choose which variable you're taking the derivative of. And so rather than using prime notation, we won't do that anymore. We'll use the notation of f sub x, meaning we take the derivative with respect to x as a variable, or we do f sub y, meaning we take the derivative with y as a variable. Now, I just told you them's the rules, but that doesn't necessarily clarify why, why that would be the rule or why that's interesting. The good news is we're about to do a couple problems that explain that to us. But at the very least, them's are the rules. So let's take a look here. Oh, well, this one is just super easy. It's just a multivariable function, and all you do is plug some numbers in. So there's no calculus in here, folks. It just says the number of cows that can graze on a ranch is approximated by the function c. What do you think c stands for? Cows. It is given by 9x plus 5y minus 3, where x is the number of acres of grass. So number of acres of grass. And so I'm going to come over here to my function. X is acres. And then y is the number of acres of alfalfa. Oops. So I'm going to not call that acres anymore because they're both acres. I'm gonna call X grass and Y is alfalfa. What's that, Adam?
Just alfalfa from Little Rascals.
Oh, yeah. Now, what does this even mean? The number of cows that can graze. What this tells us is which food is more nutritious for a cow. Let's say that I only had 1 unit of grass and no units of alfalfa. How many cows would be able to live there? I plug in 1 for X, I plug in 0 for Y. So if I just had 1 acre of grass and no alfalfa at all, what would I have? 9 times 1 is 9, 5 times 0 is 0, 9 plus 0 is 9 minus 3 is 6. 6 cows could live on grass alone. What if I had no grass and I had 1 acre of alfalfa? How many cows could I have? 2. Then 9 times 0 is 0, 5 times 1 is 5, 5 minus 3 is only 2. So what's more nutritious for a cow?
Grass.
Grass. You can feed more cows with grass than alfalfa. So as a farmer, what do you want?
Grass.
Grass, right? But the fact is, you might have farmland that has grass and alfalfa, and now this multivariable function is going to tell you how many cows you can have. What was funny?
I can't say that joke. That was too inappropriate.
Oh, you have a joke of that? Okay. All right, so there's our multivariable function. And so what am I saying? If the ranch has 30 acres of alfalfa and 35 acres of grass, how many cows can graze there?
A lot.
Yeah, so where does the 30 alfalfa go? It goes into
5. Or the Y.
yeah, the Y. So alfalfa is 30, and then 35 grass, that goes here. 5 plus 5 times Y minus 3. So that's, is that 315 plus 150 minus 3, which is 465 minus 3, which is 462? Did anyone else get that?
Yeah,
So how many cows can live?
462 cows.
462 cows. Okay. That's a pretty nice example of a multivariable function and why we have multivariable functions. Because you can make business decisions with regard to multiple variables.
So what does the minus 3 stand for? Like they lose 3 cows? Or?
Yeah, it's an interesting idea. It could be that, how would you interpret that? You might want to just consider one at a time. Let's say there's no alfalfa at all. All right? So we're just talking about acres of grass and then the number of cows. Okay, no alfalfa. Then if I have no grass either, then I'd have negative 3 cows. I don't know that that really means anything. It just means you got no cows. And if you have 1 unit of grass, 9 minus 3, you could have at least 6 cows.
Okay.
Then if you had 2 units of grass, you have 18 minus 3 is 15 cows. So what we're really looking at is, if you got no grass, you got no cows. If you got 1 thing of grass, you got 6 cows. And from there on in, the model actually goes, if it's 3, 9 times 3 is 27, minus 3 is 27, 24. So how are we actually jumping? For each additional thing of grass, what do you have? You get 9 more cows.
Yeah.
And you'll notice, what was the slope on X? 9. So really, I think that minus 3 is just going to create your y-intercept.
Okay.
After all, what is mx plus b? What does the b represent? Your y-intercept. And that's what it represents in this case as well. A negative y-intercept doesn't make any sense with cows, but the idea is that it technically starts here. And then you would need at least 1 unit of grass to have the first amount of cows you could have. Don, it's a good question, and it's not a very satisfying answer. The negative 3 doesn't represent anything in particular. You need to plug numbers into the function to calculate how many cows you can have. Okay. Because if you have 0 grass and 0 alfalfa, does it make any sense to have negative 3 cows? No. But nevertheless, the negative 3 is important to make all the other answers you get accurate. Okay, so partial derivatives. We've already introduced the idea. A partial derivative is taking the derivative of a multivariable function with respect to x or with respect to y. With respect. right. What do we have here, folks?
I feel like this is all a repeat of 213.
It's a little bit of a repeat. Yeah, this in particular, because we're doing derivatives. We have 20 more minutes, folks. You can all survive. You can all survive. Okay, in a multivariable function, you take a partial derivative of one variable at a time, treating the other variable like a constant. And we've already suggested this idea. So recall how to take the derivatives of constants and variables. So this is very important. The derivative of a number is just nothing. So if you're taking the derivative of a number or a constant, the answer is nothing. Whereas if you do the power rule, this one would be like 15x squared. Okay, we've already reviewed that. So find the partial derivative of this. Now this is where it starts to get a little tricky, and you need to go very slowly and very carefully. So everyone begin by taking your function and writing it down in your own handwriting. F of x comma y equals 7x squared minus 9xy. Now what do we want to do? First of all, we're taking the derivative with respect to what variable? X. So we're going to treat x as a variable and treat y as a constant. So the first thing you might want to consider doing, just to make that a little more obvious to yourself, we're taking the derivative, treating y as a constant. You might literally just cover up y. Right? Because if y is just a number, all you're really doing is taking the derivative with respect to x. So you could begin by just saying, hey, I'm just going to take the derivative with respect to x. I'm going to ignore y for a minute. And so this derivative becomes 14x minus 9, right? Is everyone with me there? But y is a constant, and anytime you take the derivative, what does the constant do? It just comes along for the ride, doesn't it? And so the answer is 14x minus 9y. I should demonstrate that. Let's say that you had like 5e to the x, and you want to take the derivative of that. It just comes along for the ride. Well, the derivative of e to the x is e to the x. That's not the best example. Where's an example of a constant coming along for the ride? 5 natural log of x. Remember, the derivative of natural log of x is 1 over x. So the derivative here is the 5 comes along for the ride, and the derivative of natural log of x is 1 over x. So remember, coefficients come along for the ride. When you take a derivative, they just drop down. So there we go. We just did it. We took the derivative of this function with respect to the variable x, and y just came along for the ride. That's a great way to think of it. Or, just to share one other way to think of it, you could just treat y like a number. Let's say that that was a 2, right? Y is a constant. It's just a number. So what's the derivative of 18x? 18, which is still just the 9 times the 2, but the 9 times the 2 is really 9 times y. Okay? So it'd be very helpful to remember that phrase, the coefficient comes along for the ride. Okay. So we're not done with the problem yet. We did take the derivative of the function with respect to x, but now what do they want us to do? What's that mean? Yeah, actually plug in the numbers 9 and negative 2. So everyone, very carefully now, take your 9, your negative 2, plug, so we've got 14 times x minus 9 times y. So for my x, I'm plugging in 9, and for my y, I'm plugging in negative 2. And that gives me 14 times 9, which is 126, minus a negative, which is plus 18. And so we get 144. Did I do that correct? Boy, I sure hope you're all checking my math. Now, we're at a point where we can talk about what that means. What does it mean to take the derivative with respect to x? I'm going to pull up our graphing calculator tool here, and I'm going to graph 7x squared minus 9xy. Oh boy. Okay, there we go. It's not so terrible. Look at our graph. So it's, again, our pair of pants, right? Now everyone find the x-axis. Boy, it doesn't tell us what the x-axis is.
Not the green.
Do you think it's the green one? How do you know?
I'm just guessing.
Oh, well, let's see if we can find out by just watching how they give it to us at first. So what do they give us? Yeah, I would say the green is the x-axis, the red is the y-axis, and then the blue is the z-axis. Yep, so if we take the derivative with respect to x, that means how is the slope changing in the x direction? Right? Because what's the derivative really calculating? Slope. And so when we say take the derivative with respect to x, we're saying what does the slope look like in the x direction? Boy, I really want a picture of something to share with you. Do any of you ever hike Camelback Mountain?
Height 12 feet.
All right, good mountain as well. So, let's take a look at this question. This problem. Best picture in the world. Oh, that's not bad. It's not terrible. Okay, let's look at. Oh, you guys can't see that at all. So there's a good picture of a mountain that was steep in one direction. And okay. Well, that's an unfortunate headline. We won't go there. Well, what the heck? We're just going to use this one. That's not a very good distinction, though. Oh my goodness. What'd you say, Squad Pete? Is that really the name of it now? I thought it was called something else.
Yeah, they
I
changed
forget
it.
what it's
It
called.
was like, starts with a P.
This,
Yes.
yes, Squad Pete.
Yeah.
Thank you. Okay, that is a little better. Okay, everybody, using my picture of the mountain here. All right, we're going to define along the length of the mountain. Okay, so that's your x direction. And we're going to define the y-axis as coming out at you and going behind the mountain. Okay, so I'm actually talking about it. Watch me approaching the mountain, okay? I'm moving in the y direction with respect to the mountain. Yeah, I'm going into the board and out of the board, which means I'm going past the mountain on the other side. I'm coming back on this side of the mountain. So I'm over here, I'm climbing up the mountain. Now I'm going on the other side of the mountain. That's the y direction. Whereas the x direction, maybe I'm already standing on top, and the x direction, I move this way along that gradient of the slope, or I move this way along this gradient of the slope. Okay, is that fair? Can we talk about that? That either my x direction is just, I'm literally some little guy walking on this little path right here, straight up to the top, and then I come down. But on the y direction, I'm literally coming straight down the front of the mountain, or going into the board, I'm going straight down the other side of the mountain. Now, what looks steeper? To if I'm walking this way along this line, or coming straight down the front of the mountain?
Straight down, straight down.
Yeah, straight down the front of the mountain, that looks pretty steep. Okay, don't have a lot of hiking trails that just go straight up a mountain, right? Normally the hiking trails zigzag back and forth, you have a lot of switchbacks. Okay, so right now what we can say then is that the derivative with respect to x is a very shallow slope, which means it's probably a very small slope, like 1/20th, or negative 1/20th, meaning you go down one left 20, down one left 20, down one left 20, very shallow. Whereas the derivative with respect to y, we would say is very steep, like 10/1, meaning I go down 10 steps, right 1, down 10 steps, right 1, down 10 steps, right 1. That's what we're talking about when we say the derivative with respect to x, how the slope is changing, moving in one direction, versus f sub y, or the derivative of f with respect to y, is how the slope is changing in another direction, perpendicular to it. So if you're moving this way along the mountain, it's a fairly shallow slope. And so when you calculate f sub x, you're calculating the slope in the direction of x. Whereas if you're calculating the slope in the direction of y, you're talking about coming straight off the mountain in front or straight down the back of the mountain. The point is those slopes are going to be different. And we simply now have a tool to say what's the slope like going in this direction versus what's the slope like going in this direction. Is everyone with me on the distinction? Okay, so that's what f sub x and f sub y mean. It means that we're moving in different directions that are perpendicular to each other. And so, what does the answer mean that we just got, which I just erased? What was it? F sub x, 9 comma negative 2 is what? 144?
Yeah.
All right, so everyone put that over 1. That's a slope. What that means is the slope in the x direction is 144 over 1, which remember that means up 144, right 1. When standing at the coordinate, (9, negative 2). So imagine now, 9 and negative 2 is determining your location on the mountain. You know, maybe you go to the mountain and you're 9 steps to the right of center and 2 steps into the board. What's the steepness like right there in the x direction? Versus if I said f sub y of 9 comma negative 2 means, okay, now standing at the same spot on the mountain, what's your steepness look like in the y direction? Or what's your slope look like in the y direction? This makes a lot of sense because if we can all just imagine we're all standing on the mountain right now, and let's say looking this way, the mountain is going down and away from you. Whereas if I just turn to the left, the mountain could be going up from me. And so depending on how you turn and orient yourself, the mountain could be doing something different. Yes? I wish I had a better way to visually explore this space with us. But that's what we're talking about with f sub x and f sub y. So let's try another one. We're going to try a couple more. Yeah, because if we can get through just this pure calculation business, then when you come back, we're going to be able to do some really interesting things. Okay.
Get too old for this.
You're getting too old for this?
Yeah.
Oh, and you're a young man.
20 really
All right.
gets you.
So again, we're finding now the derivative of this multivariable function with respect to y. That means y is the variable, everything else is a coefficient that comes along for the ride. So let's write it out in your own handwriting first, f of x, y. First of all, what's our variable? We're treating y as the variable. And therefore, x is just some coefficient that comes along for the ride. And again, I like covering up the x then. Hey, so there we go. We already did it. That is the derivative of the function with respect to y. X just came along for the ride. You'll notice we didn't do a thing to x. It just dropped down from one line to the next. Okay? Now we need to just plug in the numbers -3 and -4. So f, the function, you're standing on the mountain at the coordinate -3, -4, and you're wondering what is the slope like looking in the y direction. And so that would give us 2 times. Oh, this is interesting. Notice there's only a spot in the formula to plug in the x value. You know, we don't actually plug the -4 anywhere because all the y variables are away. And that's fine. It's just interesting to know. So what does that give us? -6 minus 8 is -14. So keeping in mind, positive slopes means you're looking up, negative slopes mean you're looking down. If I went onto the mountain, and I went to the coordinate on the mountain, -3, -4, and I looked in the y direction, would I be looking up the mountain or down the mountain?
Yeah.
I'd be looking down the mountain. Yep, that's what that calculation means. And my phone just went off, which means we have 5 minutes. So let's try another one. So we have a multivariable function, and oh boy, it's the chain rule. Everybody's favorite.
Good one to end on.
That's kind of low, yeah. So I'm going to write it up nice and big here. F of x comma y equals 8x plus 5y squared. And we'd like to find the derivative with respect to x. So we're treating x as the variable, y just comes along for the ride. So then, chain rule. We take the derivative of the outside, leave the inside alone, multiply by the derivative of the inside. So what's the derivative of the outside? 2. That, right? You multiply by the 2 and subtract 1 from the exponent. So that's the derivative of the outside. Leave the inside alone. And then multiply by the derivative of the inside. Well, what's the derivative of the inside, considering x is a variable, but y is just a coefficient? What's the derivative of 8x?
8.
That's 8. And then here, remember, y is just a coefficient. What's the derivative of 5?
0.
0. So the derivative of 5y is also just 0. So that's just 0.
Then the y wouldn't tag along. Situation.
Well, I mean, the y could tag along with 0.
Okay.
But 0
But
times
still
y
would
is
be 0. Okay.
0 anyway. Yep. Okay, so now we just simplify. We've got an 8, a 2, so that's 16 times 8x plus 5y. We can distribute this whole thing now and simplify it out. So what is that? 128x plus 80y. That is the derivative with respect to x. We're not done yet. Now they want us to plug in the values -5 and -4. So now if I plug in, so 128 times -5 plus 80 times -4 gives us some big thing. Which I hope someone's checking my work. I got -960. Yeah. Really. So now again, what does this mean? We're on an XY coordinate plane. So we're standing on a mountain, and we go to the coordinate -5, 4. So we're just standing somewhere on the mountain. And then we look in the x direction. So we're looking in the x direction. My slope is negative, which means now we're looking downhill. So the coordinate tells you where you are on the mountain. The x or the y tells you which direction to look, either across the board or into the board. And then the slope that it's actually telling you is if you're looking uphill currently or looking downhill currently. Now, what if I did all that work and the answer was actually 0? What would that mean? I'm standing on the mountain at that particular location. I'm facing the x direction. What's happening right in front of me?
You're looking at nothing.
It's flat. I'm actually standing on flat ground.
Looking at the sunset.
I suppose that could be. But that a 0 answer would mean I'm standing on flat ground at the moment. I'm not going uphill or downhill. I'm standing on flat ground. Which means if I'm standing on the flat ground, where could I be? At the top of the mountain. Yep. Or it could mean that I'm standing at a saddle point. Do you guys know what a saddle point is in a mountain? Away from you in these directions, but it's going up in those directions. Let me show you a saddle. I hear notebooks and such, and I assume that means that class is almost over. I have about a minute. I'm going to show you a mountain saddle. Mountain saddle. Boy, none of those are good saddle pictures.
Close to no cigar.
Heck, it should be so easy now. Mountain saddle point. Oh, there we go. Look at this one. This is a saddle point. Look, if you're standing right here, and if you start going this way, what are you doing?
Going up.
But if you start going down this way,
Going down.
you're going down. So that's a saddle point, literally the saddle of a horse. If you're on the saddle of a horse, then the saddle goes up in front of you and behind you, but your legs are going down on either side. So that's a saddle point. Okay. Well, I guess we're done. We got so. What's your homework then?
Chapter 1.
Yeah, make sure you should be done with all of chapter 1 tonight, and you can now do all of chapter 2. All right, folks.
Have you seen that video of that little kid? He's like,
Hey, great, thank you very
That's what he's doing.
much.
It's a little kid, it's a real big one. The mom has
Hey, so this way.
for a homework problem where it asks you to find an equilibrium or something like that. Right, but I think it was like a business problem. It was like negative. Like it was a negative number. So what would that mean? It just asked like if the person should continue with like the business or start the business or if they should not.
Oh, well, I mean, if the equilibrium point is a negative number, then they shouldn't do it.
Yeah, I figured that was the answer because.
Yeah, how interesting. Yeah, that would be, don't do it.
No, it was right, but I'm just trying to figure like how would a negative equilibrium point even be negative?
I'll show you. I will show you right here. Let's say that your graph, remember supply and demand, right?
Mhm.
So supply is always upward facing and demand is always downward facing. Well, so how could that point be at a negative x value? It would imply that the point of intersection, so here's your demand going down, and here's your supply going up, and this is my x-axis. So sure enough, supply is going up, and demand is going down. But somehow the point of intersection happened over here, which means the only way that buyers and sellers will be happy if -3 items were sold, which is impossible. So it means that supply and demand will never meet. What that really means is, so if this is supply, and this is demand, it means that somehow supply got way up on top of demand. So suppliers are willing to supply a lot, but demand is ridiculously low, such that the only way there'd be a point of intersection is if there's a negative number. Does that make sense?
Yeah.
Oh, good question.
All right. Thank you, Mr. G.
Thank you for the question. Hey, Michelle.
I'm gonna do office hours, just so I can get it.
Oh, okay, great. I don't have office hours today.
Oh, you know?